or?
Pointer is here.
Okay.
No, that's fine. That's fine. No,
right.
That's fine.
All right. Good morning, and I guess good evening to those of you in Europe. I'm going to take the simple things that Julian showed you and now make them a little more complicated, but at least the notation is consistent. Part of the issues we have are trying to get sigma from a rock hazard model that could be used later on for a site response study. So when we start to get design ground motions, and we want to avoid double counting of parts of the variability. Okay, in particular, studies that are going to conduct a detailed site study, like for a nuclear power plant, would want to be sure that we're not putting the variability that they're calculating in the site response into our rock ground motion model, and how do we separate it out. All we're going to talk about today is linear site response case, because that's a big enough step here as we're moving forward, and we'll deal with the nonlinear impacts in our later workshop and trying to go through this. So first, we'll take a simple case where we've got soil soil over rock. Typically, we've got ground motions on the surface at point C, but we're going to start at the bottom. So the rock ground motion, much like what Julian had used in his notation, we've got a median ground motion from a given magnitude and a distance and a style of faulting for the rock site condition. And then here we're going to have an inter-event term, okay, the A to I. So was this earthquake more energetic than average? And then we'll have an intra-event residual here. And these we had used, these got flipped, I'm sorry. This is intra-event, which we've been calling sigmas, and inters, which we've been calling taus. Having listened to what Julian said, we are confusing you too much, okay? And what I will say, leaving today, we will stop using, I think, sigma for the intra-event and just use sigma for the total. It's just too confusing. You're going to see here, looking at sigma, you'll have to know the context of what I'm saying, because it's going to start to flip. We combine this total standard deviation then of what's going in is the intra-event, the tau, and the intra-event, sigma, and the intra-event tau. We combine those two as Julian had talked about. So then we put in the site response term. We've got the average site response that the model predicts. Okay, so for example, based on VS30, what is the standard deviation? But then we also have that this site, for its VS30, the application will be different than other sites. Okay, that's what Julian was talking about. I could have two sites with the same VS30, but they're going to have different site response. Okay, and we capture that on average with this term here, xi sub s sub k for the kth site. But that's the average term. That's much like when he mentioned the attenuation model that had 80 parameters. Well, it had each site had its own parameter. That was getting at these terms. And if you have enough data at your site, you can regress for it. If I have 20 or 30 recordings at a station, I can find the average site response of that compared to my ground motion model. Okay? But in addition, now I've got variability of my site response, because every time history I drive up through here, I'm not going to get the same amplification factor. So think of this term out here as the variability of the amplification due to different input time histories, or it could be different azimuths that the waves are coming in. Okay, so we have a variability term, an average site term, and an average from our model for that VS30. So this is inherently knowable. Okay, this is randomness. Back to what is the actual aleatory term. If we go up to the top now, so on the surface, we would normally say, all right, I have my median ground motion, same magnitude and distance and style of faulting, but now I've included this amplification term here in the median. Okay, so this becomes equal to my rock motion plus that median amplification. I had an intra-event term and then my intra term on soil. And next we're going to break that down, okay? That soil intra-event term is the rock site, the B site intra-event term, the average site condition, and amplitude. So this up here is equal to these two terms plus the one on rock, Okay, now, why are we doing all this? The reason is to try to keep track of what these pieces are and make sure we're not double counting. Who owns these? All right? Who owns the variability of the site response here? Who owns the average site response term? Does it go in that rock ground motion model? Okay, so normally when we do standard deviations, we take data at the surface, we lump it all together, whether it's soil or rock, and we get a standard deviation. That would have in it the variability, the differences in the site amplification. Okay, this is a knowable thing, and it also has this variability. I think, let me see what I've got on the next piece here. So we're going to start to put together a total standard deviation at the surface, which is my intra-event plus my inter-event plus my intra on rock plus my deviations site to site plus the variability of my amplification at that site. The single station standard deviations that Julian was talking about says this piece doesn't belong here. This is knowable. And when I have 20 or 30 records, we have data now in Taiwan and in Japan and in Southern California where you've got stations that have multiple recordings of earthquakes. And from those, we can get at this term. Okay, and so this really is an epistemic uncertainty and doesn't belong in our aleatory standard deviation. This piece, and so who owns this really ought to be the site response people. If they do a site response, they would say, how well do I know this site amplification? And they may have, either they characterized it really well or not. We'll be able to tell them how well they can control this. This should be pulled out of here and put into an epistemic term. And I think it belongs in the site response group. This piece is part of site response. It's how does the site response vary given different inputs? Think about taking a shake run and putting in 100 time histories. You can get an average site response out of that for a given profile, and there'll be variability. Who owns that variability? It's really hard for us to take that out of our rock ground motions. Okay, because we can't pull this piece out. This one we can get at because we would have estimates of what is the site response from average term from site to site. We can start to pull that piece out. This piece is really hard for us to pull out right now. So when we talk about single site standard deviations, we leave in the variability of the input rock motion, and then the variability of the site response. Okay, about the average site response for that term. These were the numbers that reduced from around, say, 0.7s to about 0.6s. Okay. So, which one should we be using? The total, which includes the differences in the site amplification. For the USGS in doing a hazard mapping, they're not going to go do site-specific site response calculations. They don't want these things separated out. So for them, it's easier just to leave it all in one phase. If you're doing single station sigma, we would use that for sites or projects that are going to do detailed site-specific amplifications. So we remove these differences here. The responsibility for the epistemic uncertainty in the site amplification is part of the site response study. This comes back to, you can't simply say, I'm going to run my hazard with a single station sigma because it's lower, get a reduced hazard without paying the penalty of saying, I need to track now the epistemic uncertainty. Did I have the right average site term in there or not? The more you characterize your site, the smaller it should be, which is benefit of studies and knowledge. If you know nothing, like let's say the GS wants to use a map, they would say, well, I'm just going to have my epistemic uncertainty completely offset what the reduction is, so why bother? Right? They would then go back up here and just say, I'm going to use that value. All right? And as I said here, we are still including variability of site response due to different input motions because we don't know how to pull that term out just yet. All right, that's the easy one. Okay? So now we go to so that is considered a partially ergodic model. Okay? That is, it's traded space for time, but not fully because we've allowed the sites to be specific. Now we'll go to the fully non-ergodic model. These are things the groups Jim Brune and Anderson have been talking about for years now, and we're finally starting to listen to them. Okay, so And so in here, think about, I have two sites, sites 1 or site 3 and site 4. I have been able to estimate that site term we were just talking about because I had a lot of data at this site. Okay, so I have an estimate of the median site response, deviation from what my model would have predicted. Then I could think about earthquakes in a certain region here. Okay, and they're recorded at my site. Now, if I have a lot of earthquakes recorded here, I would have an average path term. Earthquakes from this region to my site, on average, there will be an average deviation from my typical attenuation. So I've got a simple model based on some distance metric that's average for the whole area, but all of the earthquakes from here to here tend to be, let's say, a little bit higher than average. Okay? And so then I would have a specific path term from source region 1 to site 3 that tells me that's lower than average. I might now have a different source region here coming to my site, and they're higher than average. Okay? And I could do all of those. So we're now going to talk about breaking down that intra-event variability into a knowable, potentially knowable path term that's repeatable. And then I could go to a new site and look at how does it relate to what are its path terms, deviations from our average attenuation model from this region to site 4. So I have my XIP 1,4, and then the same thing from region 2 to site 4. And I can do all of these combinations. That green map of Taiwan that you saw was drawing these for all of the different possibilities that start to show up, and you start to capture all of it. That's kind of what the people doing numerical modeling are trying to do. You could think of this as regionalization at a very fine scale. Regionalizing all the way down to a small source region to a particular site. In addition, I could look at, within this region, what about the inter-event variability, the earthquake to earthquake variability? If earthquakes in this region here, let's say the whole area I had an average of 40 bars was my stress drop. Okay, and that's how my model ended up being calibrated for how they scale with magnitude. In this region, maybe my average is only 30 bars. I still have variability, but it's centered at a lower value. This eta source region 1, sub SR1, is the deviation of the average event term from this region compared to the whole area. So if this was 30 bars compared to 40, this would be effectively the impact of a minus 10 bars. If this one was 50 bars instead of the region number of 40, this would be an impact of a plus 10 bars. So I could say earthquakes in this area are less energetic, and then there's a path effect that goes to my site. And so now I'm starting to get a non-ergodic hazard model. Now this means I need a whole lot more information, right, to start to do this. I need to be able to say, how well do I know the path effects? How well can I constrain the source effects on not just, say, 1 or 2 broad regions in the east, but how finely can I do it? But that's the whole concept. It gives us a structure where we can start to get the components that we've called aleatory in our very simple parameterizations in terms of magnitude and distance, now into something that is actually, we can take on it and make progress. So, our non-ergodic intra-event term is what we saw before. This is the same piece, right? We saw from just the site term. What we have on the surface of soil, I had what was on my input rock, I had my average site amplification, and the variability of the amplification term. Okay? I can now break this one into those two pieces. This is the path term from region, source region L to site K, that's this term. And then here is what's left. This is the variability that's left about just wave propagation from that source region to this particular site. So this would be, on the right, this xi sub b is our actual aleatory part here. Okay? This term is potentially knowable. This term is potentially knowable. This is an aleatory piece as well. All right? So now we're taking what was treated as all aleatory and saying there's two parts of this which were actually epistemic pieces. Okay? So this we are using now a sigma sub s, the site-to-site variability, a sigma sub delta amp, and I will tell you by tomorrow I'm going to change from sigmas here to, when we went from intra-event and intra-event, we just went from S to T, sigma to tau. So T to U, whatever the Greek U is, I think we'll put here so that we've got something that's different from sigma and leave sigma for the combined effect because it's just too confusing right now. All right, because now I'm back to, I have a sigma P and Julian also had a sigma P, a different one, right? A sigma parameter, and we'll change that one as well. So this is related to the path. This is how much the path changes. Okay, what are the systematic differences in the path effects that are potentially knowable? This is really the aleatory part of the path effects. We have then, for the inter-event term, our Foley non-ergodic approach. We've taken our inter-event standard deviation, now have an additional subscript for the region it's in and the earthquake. Okay, and now I have the average deviation from average for that earthquake region, and then the variability of the earthquake term within that region. Okay, so we're getting all of the components down, and we can now start to attack them one at a time. So we end up with our ergodic assumption has all of these pieces in it. Okay, so initially we just had sigma squared and a tau squared in here. Now we have 2 pieces of the tau, and we've got 4 pieces of the intra-event. So 2 inters and 4 intra-event terms. If we get rid of what we say is really not aleatory, what is not randomized but potentially knowable, we're down to just 3 terms. Okay, so we would say this is knowable, and this term is knowable, and this term is knowable. All right? That's how you get from here to here. You go from the 0.7s to the 0.4s. That's a huge change. The penalty is increased epistemic uncertainty now, because as soon as you pull these out, these 3, the sigma P, sigma S, and tau SR, are now epistemic uncertainties that you're going to have to deal with in the logic tree. If you have ignorance and no information to constrain these, the epistemic uncertainty will offset this reduction and put you right back to where you were. But if you start to have data, you start to have numerical simulations, whatever, that can start to constrain these things, then we can actually make some progress. All right, the other piece of this was simulations. And I'll go and try to now put these pieces together. Okay, Julian talked about this box we had, our 2x2 box from the Toro et al. Paper, breaking the aleatory into modeling in parametric terms. Okay, the reason we do this, and because I already had recognized I had a problem with sigma P, I have now called it sigma par and sigma mod. These are truly sigmas. They're part of the total standard deviation, not just the inter or the intra. Okay, we get this piece. When we run numerical simulations, we can run it for lots of different input parameters. I could say, what do I get with 20 bars? What do I get with 50 bars? Okay, what if I use what other aleatory variables would we have? So we would vary those inputs that go into it. If I had a finite fault simulation, I might be varying the slip pattern on the fault. I could vary the rupture velocity as it starts up and slows down. As I run these with a lot of forward modeling, I'm going to get out a range of answers. Okay? And we call that our parametric variability. But there's an additional term here that we need to track, and this is what we've called our modeling term. And that is, my model doesn't work exactly right. Okay? Even when I calibrate all of the inputs as good as I can make them, I'm still going to have a misfit between predictions and observations from past earthquakes. Okay? And so we call that misfit there our sigma modeling. And then the total aleatory variability from a simulation combines this term and that term. If I thought of a simple empirical attenuation relation, I have no term here, okay, but I have variability up here that's just our misfit from our data. As I start to add more features of the model to better predict observations on the physical sense, you could think of, like, for example, directivity. If I start to add varying directivity into my model, I could vary the location of where the earthquake starts, and then I start to get a parametric term. That's what we do when we run hazard, for example, with Somerville's directivity added into our hazard analysis. We're starting to move stuff from unexplained variability to explained variability. You like to be down here because we know what the cause is. Up here, we've thrown up our hands and we say we don't know why it didn't work, but that's just the limits of our model. Okay, so we go from ignorance and randomness here, or unexplained randomness, to explained randomness as we move down here. So as we move more and more to more complicated or improved physical models or simulation techniques, this should be getting smaller, and this should be getting probably bigger as we start to have to randomize more of the pieces. In the end, the combination, the total, doesn't change that much. Okay, that's that stable piece again. The only place it's going to change is if we go to that whole non-ergodic approach. Okay? So then we start to get to the pieces. We have epistemic uncertainty. That is, did the model actually work? So Julian talked to you about this sigma sub mu, the epistemic uncertainty in the median. You could also get this by running alternative models. You know, we might have 4 different simulation techniques we could end up using. And then there's epistemic uncertainty in the value of this sigma mod. How well is that constrained? That's part of our sigma-sigma term. Okay, this depends on data. If I have only a few data points, this will be highly uncertain. As I get more and more validation cases, I get to constrain this thing better. The parametric part, I want the constraints on the median inputs. How well do I know that the median stress drop was 40 bars? Okay, that starts to contribute to my sigma sub mu. How well do I know the variability of that stress drop? Could the stress drops range from 10 to 100 bars? Basically, what is the standard deviation of the stress drop? And that contributes to our uncertainty whether how well we constrain the variability of the stress drop contributes to our sigma-sigma term. Okay? Now, that's the easy part. So now I was trying to, now how do you take that other breakdown and force it into these boxes? And they don't fit uniquely into each box. Okay, so there's so I could say what goes into modeling aleatory. Part of that sigma, my inter-event variability at the top with all of those pieces, and I didn't try to break it into the 5 pieces yet, goes in here. And I said partly goes in here because depending on your model, in an empirical model, it's all here. Okay? In a simulation model, some of it will be here, and some of it will be down here, depending on how we have parameterized the source. The inter-event standard deviation is all down here in these models because these have been optimized to fit the earthquake as best as possible in the fitting, and then the rest is our prediction of variability of future source processes as it drops down into here. And then the same thing here, we've got our uncertainty in our sigma mod is the sigma mu, and our uncertainty in how well did we get this parametric variability from all of those combinations. I actually had made a plot where I put all of the 6 pieces in here, and it was completely unintelligible, so I won't push you through that. But really, we have to start to figure out that breakdown into these 6 basic components and how we're going to get at them. If we're relying on numerical modeling in the East, which we're going to have to, we need to work in this framework here so that we're capturing all of the pieces without double counting. The problems we face on this is correlations of the inputs. Empirical data is nice because it naturally has the proper correlations in it. On the simulations, I really need to worry about correlations. If I blindly propagate all the uncertainties as uncorrelated, I get really big standard deviations coming out. And this can end up being much bigger than our empirical values because it misses some of the correlations. Actually, I did show that. I'm going to jump because this is, I think, too much for you to see. Well, how all of these pieces, I'll go really quickly. So sigma S drops in here. Sigma amp is up in the modeling term. Part of the sigma naught is here. And the sigma p, if I had a simple crustal model, like a flat layered model, then I'm not going to pick up path effects, right? But if I have a 3D geologic structure, then path effects are going to get picked up into my parametric variability term. And the uncertainties come through. That's more than you need to see. So, should we be using single path sigma? We talked about signal station sigma. Yes, it's appropriate if you're going to do a detailed site response and you will capture or take the penalty for the epistemic uncertainty in how well you can characterize the site. This is really similar to very fine regionalization. Instead of dividing the eastern U.S. into 2 regions or 5 regions, every small source region and every site has its own attenuation model. Okay? Probably not practical All right? But this is sort of the limit of regionalization. Broad regionalization provides some of this reduction, but not as much. Okay? These are big jumps, though. I mean, these are from our data. We see potentially going from a 0.7 down to a 0.6 from single site is great to a 0.4 really tells you what the standard deviation should be. We have this big additional epistemic uncertainty in the path terms, and you have to include that. So how can you get at that? At least this gives you a framework that fits pretty well with numerical simulations for making progress. And our questions that we're going to get at, can I constrain this path term from small earthquake recordings? If you can, then there's a huge potential here. If you can't, then we'll just leave it all back in single station sigmas. But this is what we need to look at. Can we get at these pieces? So with that, we did have a working meeting on sigma in September of 2009, and I'm going to run through quickly what some of the tasks that we identified were. Some of them fit into what this framework is we're talking about. Others have not, as we're just sort of pulling all this stuff together. And some of the results will be shown in the talks this afternoon. So first action item was dealing with magnitude dependence of the standard deviation. What you saw, Julian talked about some of the NGA models were magnitude dependent, some were not. Should this be included or not? And so we're looking at some causes of this. In particular, adding small magnitudes. Linda and Brian are going to talk about these pieces here. Can we see magnitude dependence in the NGA models? A key issue was that in the NGA models when we did this, the magnitude dependence for those three that included it, those three models also included aftershocks. That's where the magnitude dependence came from. If you didn't include aftershocks, most of the little earthquakes were gone, and you were not required to have magnitude dependence there. Okay, so now the question is, were the aftershocks representative or not? And that'll be addressed. So there'll be a comparison of magnitude dependence from main shock data with a lot of little earthquakes to try to evaluate that. I will talk about later this afternoon, there's basic question, applicability of an empirically based sigma, say from active regions to stable continental regions. Should they be the same? There's a real advantage of using empirically based sigmas, and that this is all the correlations I was talking about. They are naturally in that data set, okay? And so that we don't start to build up too many or too large of a sigma because we didn't track all of the negative correlations and how some of the things act. So I'll talk about this as well, about an evaluation that was done for EPRI, looking at applicability of Western U.S. sigmas to the east. And something that we haven't done, but as well a second check would be, we could be looking at, are the standard deviations from small magnitude earthquakes in California, particularly the intra-event terms, the path terms, similar to those from the east. If they're similar at small magnitudes, we can have some justification to believe that maybe they'll be similar for large magnitudes as well. Okay. Really, this gets down to, is the crustal structure differences or wave path differences in the east greater than they are or less than they are in the western U.S. where we have more data. Another action was stability of sigmas. We're not going to present this. There's a bunch more work that's starting to happen on this. That is, once we start to look at other regions, we can look at California, we can look at Japan, we can look at Taiwan, we can look at Turkey, areas where there's a lot of data and they can get the sigma for that region. How stable are these empirical estimates of the sigma? What is coming out is the sigma totals are not that stable, but the single station sigmas really are. We're getting much more common values of single station sigmas. The implication of that is that there's a different level of variability of the site terms in, say, Japan than what we have in California. Okay. The other part, what is the stress drops, stress parameter distributions? This gets back to that inter-event parametric term. Okay, so sigma parametric for intra-event variability. If we look at stress drops, what is the distribution of stress drops, or here stress parameters for earthquakes in the east. Then we can propagate that through to get the standard deviation of the ground motion, the intra-event parametric standard deviation. And there are issues of, so Bob will talk about that, issues of what do we do with Saguenay. I mean, that's one of our recurring problems. One of our best recorded earthquakes is deemed anomalous. All right, that's a tough situation to be in. The depth dependence is also another issue that we'll get to. Propagating the magnitudes and distance conversions. Distance conversions were made for hazard calculations. And Gabe will talk about this, and I'll talk about that. Essentially, did we do this right? And this gets back to correlations in parameters. Okay, when in the Toro model of 97 and in the EPRI 2004 report, corrections were made from essentially a point source distance or a rupture distance to a joiner bore distance. Okay, and said the joiner bore distance doesn't account for depth effects, therefore we have to have additional variability to capture that. But if there's something that counteracts that, is correlated with depth, then we're putting too much variability in, and that will be talked about. Oh, I missed one. Magnitude conversion has been a problem in the past. As Larry mentioned, source characterization will be for MW. This is not an issue for us, so we're not going to be dealing with magnitude conversion problems. Outlier data, again, what do we do with outliers, not just in the Saguenay earthquake itself, but outlier datas. There was, Julian alluded to the approach of the Italian data set where you kind of get rid of the bigger ones and try to explain them away. Typically, most things you try to explain, every site is special, right? And so if I handed you a record, you would explain away that particular record in some way. It's the source. It's the 3D wave propagation. It's the site response that was there. I mean, each one you can find something special for. So we need to find something simple enough that if you're going to remove outliers, it's got to be based on an approach that can be applied to all of the sites, not just because it's the high one. Okay. Single path sigma. So we are talking really, a question happens is, fundamentally, do those little earthquakes that we might have, are they informative? If we get their path effects out, because we can do a regression for little earthquakes and we can actually estimate that psi sub p term, okay, is that informative for bigger earthquakes? Now, that's heresy to the seismologists to say it's not. I mean, if you're doing empirical Green's functions, that's what everything is based on, that it is informative. But what we want to do is take small earthquakes recorded near large earthquakes in California, Japan, and Taiwan, and then say, if I know those path terms, okay, from the small earthquakes, how well do they predict the intra-event residual from the bigger earthquake? And are they informative? If they are, then we got a place to go. If not, we don't. Essentially, does weak motion tell you something about the site and path terms? That's really what we're asking. I believe that's it. The last thing, epistemic uncertainty, and this is more than median. It's also the whole model, I think, both the median and sigma. Is in the ground motion model, the sigma mu, are our models capturing the range, okay, of what is really out there or not? And this comes back to our problems we've had in the past. The models that we use, okay, in hazard analysis are based on what's been published or what's been put forth. But as more information comes out, more people publish models, and now my epistemic uncertainty gets bigger, right? So we've had the continuing problem of the more research we fund, the more models we get, the bigger our uncertainty, right? So we're in just we're not making progress, we're going the other way. What Frank will talk about is a very innovative way to start to look at the space that your models have captured. What are their similarities? How different are they? And are they inclusive, and how might we even fill in between models and that sort of thing. So that's for this afternoon. And I believe now I am at the end.
Great. Thank you very much. Very good. Thank you very much, Noor. Very nice presentation. Now, if you have a few minutes for questions, if you have any questions, Linda is going to pass you the microphone. Questions? Everything is clear. Yeah. Armin.
Yeah, I'm going back to earlier discussion about the form of the model and the number of parameters. I appreciate what you said, that these are not entirely empirical models, but models derived from some physical considerations. But it's also true that at the end you have to do some fitting through regression or other means, and there is uncertainty in the coefficients of your median model. And so there are, of course, ways of determining the significance of each of those terms. If you have too many parameters in a model, you end up having coefficients, estimates of coefficients that are highly uncertain. So statistically, there should be a way of saying when a model is just too complicated.
Let me interrupt you and say again very clearly, we are not building statistical models. And that sounds contrary to the empirical approach. In the end, in the regression, very few terms are actually determined by the regression fit. So for example, in my model, you might see 20 terms and go, how can those be? Okay, at least half of those are constrained. Right? They're either fixed by what some other analytical model has said, the scaling is fixed, or something like that. So it is really very different from the idea of let me fit the data. And the reason for this is our main interest is outside the range where the data are. Okay, I'm interested in magnitude 7s to 8s at 5 kilometers in California. Well, that I could just say, let me take my 5 or 6 data points that are relevant to that and fit it, okay, or say this is the average value. We're taking, really taking trends that we got from numerical simulations of site response. We had numerical simulations from finite fault simulations that told us how do things scale with magnitude as you go above. How do we move from, we have good data at 30 kilometers from a magnitude 6.5, all right? There I can tell you what we're doing. It's really how do we move off of that? So when you start to look at the statistical uncertainty, you have to track how many of those parameters did we lock down. And a lot of them are simply constrained based on other either simulation evidence or physical evidence, or in the end, a judgment, but not much more than the slopes where we have distance, data at large distances, and the average level is really coming fundamentally out of the regressions. There's more constraints in this than you believe, I think. If you sat down, put in my equation, and tried to run a regression for all 20 parameters, you couldn't do it. It simply would not converge. So this is probably a different topic than sigma here, because as we said, in the end, these tweaks are really how do the model extrapolate outside the range of the data. I want to be able to say my model is going to produce a value I believe in at 1 kilometer from a magnitude 8. Okay? I have no data on which to base that. But you guys as engineers won't let me say I don't know, right? When you get asked for the design motion. I have to give you a number. And that's really what this is all about. It's very different than statistical models. Otherwise, we could hand this to the statisticians and say, do it. Give it to a grad student. And that would be a complete disaster. It's happened. Yeah, it has happened. And you get part of the range of sigmas runs you from 0.1 to 0.9 or whatever those numbers are, is back to just handing this off to someone who isn't thinking through what are we building as a model. So we'll have plenty of time to talk about median models. That's really not our topic today. But I want to leave you with the idea that that complexity was not at all driven by reducing the standard deviation or saying, is that parameter in that model constrained by the data? It's, do I need that parameter so that my model will extrapolate the way I think it should? That's really what it's all about.
I must say this was much clearer explanation.
Okay.
More questions? Okay. Yes, sir.
I was wondering if there's going to be any studies on the ground motion spatial correlation as a result of these deconfigurations of the aleatory and epistemic uncertainties?
The answer is well, yes, you have to. Okay, so as soon as you start to look at if you're going into this more complicated breakdown, then now you have, let's say, those path terms we're talking about. What is the spatial correlation of those path terms? How big is a region for which the path effects are similar? Okay, and although here I have little regions that are shown, you actually need this, if you're going to do it formally, on a continuous basis. Okay, so if they're 10 kilometers apart, maybe they're similar. If they're 30 kilometers apart, they're going to be more different. Okay, but that will. So the short answer is yes, there will be an issue of addressing the spatial correlation because you have to in this kind of a framework.
So would you put that in your action items?
Yes, and we're going to add these to this afternoon.
No, in fact, that's a good point. The action list is tentative, and in fact, that's very good. So more things that we get comments from the audience, we are going to add it. That's good. Afternoon, we are going to finalize the action list. Any other question? Discussion? Question, discussion? Okay. So let's take a break.